So first of all, thank you to the organizers for giving me the opportunity to present our work here. So I'm Robin Kooistra. I'm a postdoc at Kafuli IPMU near Tokyo in Japan. And I'm working in the group of Keegan Lee on this project on using Lyman Alpha forest tomography to study proto-clusters, and in particular to study the heating in proto-clusters. Sorry, this is a brief outline of my talk. So I'll start just introducing some of the things that I'm talking about. So Lyman Alpha forest tomography, then the Clamato survey that we're mainly focusing on in our group. And then I'll introduce cluster preheating and our simulations. So let me start with the Lyman Alpha forest. So for those of you who don't know, the Lyman Alpha forest is a feature that pops up in high redshift objects in the spectrum. And it's bluewards of Lyman Alpha, of the Lyman Alpha line here. So as the Lyman Alpha line redshifts, you see that the emission bluewards of Lyman Alpha redshifts towards the frequency of Lyman Alpha, and then the local hydrogen gas will absorb the emission, and then you start seeing these peaks pop up here in the spectrum. And this absorption, basically every peak here is sort of like one gas cloud along the line of sight. And the absorption optical depth depends on the neutral fraction and the underlying density field to some power. And you basically see, like, if you have very dense structures along the line of sight, you'll get very deep absorption, etc., etc. And in 2014, Keegan Lee showed that you can also use Lyman break galaxies as background sources, and you don't just need high redshift quasars, which people were using before to study this. And if you have enough of these objects in the background, you can actually reconstruct the underlying absorption field in 3 dimensions. And this is the technique known as Lyman Alpha forest tomography. So if you have a dense enough distribution of sight lines, you see the more sight lines you add here, the more structures you start to be able to resolve if you do Wiener filtering. And then once you have like multiple sight lines, in this case 124, you can already start reconstructing some 3-dimensional structures like overdensities and maybe some filaments already. This is an early data release, but there's better data available right now. So one of the first surveys to really use this technique in detail, and in particular to use this technique with Lyman break galaxies in the background, is the Clamato survey led by Keegan Lee here at IPMU. And it's a survey with Keck, with Elra's instrument on Keck of the cosmos field. And basically they have a mean transverse separation between the sight lines of about 2.5 megaparsec/8 at redshifts of 2.1 to 2.5 for the Lyman Alpha forest. So this gives you a pretty massive volume, so you can really start studying the big structures, large-scale structures in these kind of surveys. And the data release is now public in the 2018 paper. And one of the nice things, and I'll come back to this in a few slides later, is that we now have dark matter density reconstructions of the cosmos field as well. So we can use that to our advantage. So this is the latest, or at least the current available data release of the Clamato survey. And you see in the white dots the galaxies, and then in blue is the absorption. And you see basically wherever you have an overdensity in galaxies, you'll also have an overdensity in the absorption. So this really follows the large-scale structures, and you can find some really big proto-clusters in here, and also perhaps some filaments, but analysis is still underway. But these are some examples of some of the massive structures that we find in here. So there's this proto-cluster at redshift 2.1, which was first found in the Seaford survey. And you can do some large-scale structure analysis already on this. So here I'm showing you some work that's in prep by Benjamin Horowitz, where you can see in green the filaments, in white the galaxies, and then the nodes. You really see these massive nodes in this network of filaments there. But also the big structure in the survey known as Hyperion, which I think a lot of people that are here have studied and maybe we'll discuss as well today. So this kind of survey really gives us a lot of opportunity to study the proto-clusters as well. And as I said, we now also have the dark matter density field of this cosmos field. And this is work done by Metin Atta. where he uses his cosmic birth code to basically infer the density field of the cosmos fields through some Bayesian inference, and he can do this directly on the light cone. So it really allows you to infer multiple realizations of the underlying density field that each reproduce the structures traced by the galaxies. And you can take into account the radial angular selection functions of each of the surveys. And if you take the mean of all the realizations, then you see that where you have data, you start recovering all these major structures, the proto-clusters. And outside of the survey area, it all equals out to the cosmic mean density. And since you have many different realizations that produce the same structures, you can use the single realizations to estimate some variance on this map. So that brings me to the cluster preheating part of the talk. So cluster preheating, for those of you who are not familiar, is something that was introduced already back in the 90s. And it's based on these observations of low redshift clusters of the X-ray temperature versus the X-ray luminosity. And people were finding that from what they were expecting for these structures to evolve by self-similarity, which would result in a slope of 2 in this diagram, people were finding that the actual observations were much steeper than this. And also more recently in studies of the entropy in these regions, people were in these clusters, people were finding that there's excess entropy from what can be explained from self-similarity in the small radii and also the intermediate radii of these clusters. So this suggests that there's some extra heating going on, and people suggested that you inject extra heat at higher redshifts, around 3 or so, into these clusters, and then let it evolve to the low redshift clusters that we see today. And this heating could be feedback from stars or AGN, etc. Yeah, this is still something that people are discussing. So we wanted to add to this by working on zoom-in proto-cluster simulations with the goal to see if we can use the Lyman Alpha for tomography to put some constraints on this. So Shiaki Inoue from Tsukuba University ran a lot of simulations for us using the Arepo codes. And then he turned off all the feedback, star formation, and the cooling effects. And then at redshift 3, around these massive clusters, he starts injecting, according to the scheme from Borgani in 2001, he starts injecting energy into these systems in all the particles with a gas overdensity of 5 or higher. If their entropy is below a certain floor value, and we chose 4 different ones, then the particle the temperature will be raised of the particle to get to that floor level. So the entropy in this case is defined as temperature times the electron density to the power -2/3. So this is the main thing that we're the main results of our simulations. So we're looking into the flux over density versus dark matter density. And flux over density in this case is defined as the flux divided by the mean flux -1, where the mean flux is the observed mean flux, which in this case we chose the observed values by Becker. And then we extract simulations, we extract Lyman alpha spectra from these simulations, normalize the fluxes, and then we make this plot here. So basically what you see is if you start injecting energy into these systems at redshift 3, then at redshift 2, which is these plots, you start getting a tilt here in the distribution of delta flux versus delta dark matter. And the more entropy, the higher your entropy floor, the more the tilt goes upwards. So we can measure the slope on the delta dark matter from 1 to 3 in this plot, and plot the difference between the two as a function of the redshift. And we see that there's an evolution in the difference from no injection of entropy. So this is the slope between 1 and 3 in dark matter density, when in the case where you have injection, minus the case where you have no injection. And you see that there's some evolution. And the most striking thing is that basically at the lower redshifts, you have the bigger difference. So it's really something that evolves towards lower redshifts, and also for the different masses of the for the clusters. These are one example of injection that we did, but we also wanted to perform some higher resolution simulations because these previous simulations were not resolving all the small scale structure of the observed Lyman Alpha forest. The problem is our entropy injection scheme then kind of breaks down and our clusters were exploding. So Renwei Chen from Princeton developed some new injection scheme for us, where instead of setting an entropy floor, we now inject energy of different amounts into each particle in the simulation at redshift 3. And then you again get roughly the same trends that you see here, that we saw before in the lower resolution simulations as well. So that's promising that things work both in lower and higher resolution. But when we look at the evolution of the difference between the slopes, we see that there might be actually some difference between lower mass and higher mass clusters. So the higher mass proto-clusters, they evolve in the same way as we saw before, but it seems like there's some flattening going on. So the difference between the different contours is not as large, not as significant, with redshift for the lower mass clusters, and we're not sure yet how to explain that. And this is just showing that again for all the clusters that we have. So here the different colors show the different proto-cluster zoom-in simulations that we did. And you see that the lower resolution, everything kind of ends up roughly in a similar fashion at redshift 2, the highest values. But for the energy injection scheme, we seem to be getting some kind of split. So this could maybe be a sign of some this could be something that we could explore in more detail, basically, to see if this could be some significant feature of this kind of energy injection or not. But we're still working on that, so stay tuned. And that brings me to my final slide. So I hope I've convinced you that we can use surveys like Clamato to study heating processes in proto-clusters at redshift 2 to 3. And we showed that if you inject some energy into these systems at redshift 3, then at redshift 2, 2.5, you can really start seeing some signatures of this heating into in the IGM of by using this distribution of delta dark matter versus delta flux. And yeah, the next step that we have now is, of course, to actually use the data. And since we have these birth reconstructions of the dark matter density fields, we can really start putting this into effect for data, basically. So stay tuned for that.
是不是有点问题？
That was what I had to say.